Hello everyone, my name is Aditya and this research is a joint work with Kyushi and my advisor Professor Kang Ji Lu. In this talk, I'll be talking about some of our contributions. I'll be sharing with you all our contributions about our tool which we use to develop missing check bugs in the OS kernels. This tool is not only scalable but is also context aware and interprocedural. Some of the techniques that we use in this tool are identifying critical variables, identifying peers that share similar context and semantics. We also propose a technique where we reduce the number of the potential targets for an indirect call. Using the techniques in the tool, we were able to find 278 new missing check bugs in the latest version of the Linux kernel. And out of them, 151 were confirmed by the maintainers and 134 are already existing in the mainline version. So, we all know that operating system kernels are an important piece of software, and because of their complexity, they are often error prone. To ensure that the system is doing as expected, developers often enforce numerous security checks to guarantee the state of the system. According to our study, the Linux kernel has about 400,000 security checks. To reuse some of our previous work, we define a security check as a following set of patterns. So a security check is basically a conditional statement which has at least two branches. At least one of the branch does some kind of error handling, and at least one of the branch should do the normal execution. A conditional statement in which all of the branches are either error handling or all of them don't have error handling is not considered a security check. The following slide shows some of the cases, some of the benefits of, or you can even say some of the reasons why you use a security check in the Linux kernel or any OS kernel. So despite you have so many different classes, the problem is this: security checks themselves are buggy. I mean, who would have thought of that? But the problem is this: the most common case that we see in a security check bug is that the entire security check is missing, right? So a scenario in which the intended security check is missing in the lifetime between the source of the critical variable and the moment the critical variable is being used, you basically call such a scenario as a missing check bug. Now, why should we detect? Now, given that I told you how prevalent security checks are and why we need to, I'll tell you why we need to detect these missing check bugs. So we conducted an empirical study of CV vulnerabilities over the past 2 years, and we found out that about 60% of the vulnerabilities were patched by either adding a new security check or they have updated a security check. So the impact of having this missing check bugs are not having an impact. The impact of not having this security checks are you can have denial of service, memory corruption, information leakage, and many others. A straightforward approach to detect missing check bugs are to enumerate all the possible rules and notify the categories, notify the classes, and detect these bugs. However, this technique is not scalable, and you cannot generalize this rule enumeration to all classes of bugs. Instead, we consider an alternative approach called cross-checking. This is basically a statistical analysis method where you don't care about what the ground truth is. You just assign the majority rule within a group to the entire group, and then you say any deviations from this rule are basically bugs. This idea underlies the assumption that the kernel in general is correct, and bugs are basically the outliers in that. To drive home this point, the following figure shows you what a deadbolt is. So let's take an example of 10 doors, and out of this 10, 9 have a deadbolt and 1 doesn't have a deadbolt. So you can more or less say that the one that doesn't have a deadbolt is likely to be a bug. Unfortunately, it doesn't consider a scenario where the door which doesn't have a deadbolt might be using an IoT smart home security device. So cross-checking doesn't consider this type of information in it. Now, despite the simplicity of cross-checking, it's not straightforward to use it right away for detecting bugs. We identified at least 3 challenges in this approach. The first one is scalability. How do you know which of these variables should I start checking for? We think that if you identify what the critical variables are and just check them, I think we can solve scalability. The second case is similarity. What do you compare against? Like, you want to get a group, that's good, but how do you know what constitutes a group? So this is one of our major contributions in this paper where we identify similar context pairs. And the third case is granularity. You want to model your conditional statements at an appropriate level. For example, if you think that a conditional statement which is checking less than 0 and a conditional statement which is checking less than 10, you don't want to model them as 2 different constraints. You want to get an optimal granularity level. So we propose to solve these challenges, we basically propose a tool called Crix, and in a high level, we solve this in 4 stages. I'll be describing these 4 challenges in a short while. To solve the problem of scalability, we basically use 2 insights. The first insight is any variable that is checked is more likely to be critical. And the second insight is often variables propagate their criticalness in its neighborhood. So our approach is basically to identify these checked variables, and then we want to find out the source and users. So in the code snippet that you see, the first line shows the source, the if condition is the check, and the last line is basically the use. So we want to basically identify this type of code snippets. The second case is to identify similarity. Okay, I think we lost some code that side, but yeah. So why do we need similar pairs? The first thing is, since we are using a statistical method, it's important for us to have a large set so that we get better results. Accuracy improves by having a large training data, you can say. And it's also important that you compare apples for apples, not something like, you want to get accurate context and semantics. You want to compare pairs that have same properties. The observation is this. In the Linux kernel, similar context pairs are often coming from either call instructions, be it indirect calls, or the return instructions. Blindly performing a slice would lead to path explosion problem. So we had to identify this by a certain set of properties. In the following 3 figures, you see that whenever you have an indirect call, based on the arguments, you can say that all the callees are potentially similar context pairs. Similarly, we have return instruction, which is basically the return value of a function, and then you have the direct call, which takes the parameter of a function. The other 2 cases are discussed in the paper, but I would like to spend some time talking about indirect calls because of their importance and the prevalence in the Linux kernel. Now, why do we want to reduce the targets of an indirect call? The first thing is the Linux kernel is huge. You have about, I would say, close to 60,000 call sites of indirect call. And because we are using a static analysis technique, the call graph precision is important for us to get accurate results. Now, we decide pairs of an indirect call based on the type of arguments they take. If the number of arguments the number and type of arguments are same, we basically assume that these are similar pairs. But as the current techniques show that just by the current, at least the state of art is to use either points to analysis or function type matching. We identify that they are prone to having a huge, they're prone to having a large number of false positives. So in this approach, our approach was to basically use two-level type analysis. What does this approach do? The insight, the observation is this. In the Linux kernel, at least 90% of the indirect calls are basically stored in a struct variable, and often these are interfaces. They are the interfaces which are used to implement them, all the similar context functions. You can think of them as something of if you take an example of a file system, you see that the open system call or read system call across file systems, they basically do the same thing, but they may be implemented in a different way. So going back to our approach of two-level type analysis, we rely on function type matching, which basically eliminates all those indirect calls which don't have similar arguments or similar type of arguments. The second layer is struct type matching. In this case, we basically identify in which field was the struct loaded, in which field was the function pointer stored, and how is it being loaded while you are dereferencing the function pointer. To make this approach sound, we use escape analysis, and we also fall back to the basic first level to function type matching when we are unable to decide which field is the function pointer from. Okay, so the third, after you generate these peer slices, we use modeling constraints where we determine at what granularity you want to reduce, at what granularity you want to model these conditional statements. After you model these constraints, we use a single hyperparameter in our system called relative frequency, which we assign a value of 0.15. Relative frequency is basically the ratio of number of peer slices which miss a security check to the total number of slices. We determine this value by performing an empirical study of security patches from the Linux kernel, and we chose this value where we minimized all false negatives, but we were okay with certain set of false positives. Given that I've described the principles behind Crix, we implemented them as a set of LLVM passes. The code has about 4.5 thousand lines of C++ code, and it took about 64 minutes to complete. Because Linux has a different set of architectures, we only focused on x86 architecture, and it uses an all-yes config. All-yes config is basically trying to maximize the number of potential cases you can cover, and we identified about 804 bugs. Also, we use ranking heuristic to prioritize which bugs we want to look at. So, given that we have run the tool for 64 minutes, following are the results that are interesting to you guys. So out of the 278 new bugs that we have found, 134 of them were already applied to the mainline, and about 100 of them were confirmed or fixed within 1 week of submission. Further, we have about 195 bugs that were found in the drivers module, and over 27 of them have more than one bug within a single module. I mean, this still falls back upon the previous research that drivers are still buggy. Also the latent period, which says the time it takes from the introduction of the patch to the time it takes to fix it, it's about 4 years and 7 months. And 10% of the bugs have about 10 years. Now this may seem a bit dramatic, but since Crix is a static analysis tool, it's inheriting all the limitations that a static analysis tool can have. However, I would like to mention one of the limitations that we basically are basing our tool on. It's determining the context. So whenever you have a critical error that has happened, and in the cleanup path, if there are functions that are cleaning up, the maintainers have very reluctant to add a security check in this path because they do understand that if the system is crashing, adding a security check is often the least of their concerns. So in this talk, I basically am reiterating the fact that security checks are critical, but they're still prone to bugs. I shared with you the idea of finding, modeling, and cross-checking peer slices that have semantic and context-aware properties. And we have about 93% reduction in the indirect call targets compared to the existing techniques. And we open sourced our code, and it's available at this link, right? So with that, I'm happy to take any questions.
Thank you. This is a very interesting topic. I'm always interested in sort of simple ways of finding trivial but common issues. One particular issue that is fairly common is where a variable is checked but after it's been used. Can your method be extended to handle that case as well?
So the question is, you use and then you check. In that particular case, the source is not basically at the check. It's somewhere before that. You could think of this as an uninitialized variable. Would you say something like that? You could think of something as a variable that's coming from the user space. Would that fit your description?
An example that has been common in the kernel in the past is where you get a pointer and you do something with it, and then you check if it's null.
Right. So yeah, that would probably fall in the case of the source. Yes, we do handle those cases, and our tool does handle those cases.
Cool. Do you think this can work on things other than the Linux kernel?
Other than the Linux kernel, you mean? So we actually applied this tool to even the FreeBSD, but at the time of submission, we couldn't submit the patches, so we didn't mention any of this. But this technique is actually scalable to it's applicable to any OS kernels. FreeBSD still uses the same idea of structures. It still has the same concept of security checking. Go on.
Cool. Thank you. I look forward to trying this.
Sure.
So can you tell us a little bit about those bugs? Because they're like 800, then you went to like 280 something.
Yeah.
Were they actually serious? What's up?
So the idea is this. Consider an example where you're allocating memory with kmalloc. There is some kind of context which wasn't actually captured. So you can say something like, if you look at the arguments, there is an argument called GFP no fail, where the memory allocation is done without any failures. Like there is the memory is allocated in an atomic context. So most of these bugs, what we have found, they seem valid to us, but when you put the same question to the maintainers, they would be suggesting that these bugs don't basically occur in the real time. So yes, tool has false positives, but I would also like to mention a second category which wasn't mentioned in the talk, or it's not even present, or it was just vaguely present in the paper. Because we are doing a two-level search where we search from source to check and then use, and as well as from use to check and to the source. We do two ways of checking the code. There were many instances where these 804 cases had duplicates. Like the same bug was reported in two directions. So I would say probably they constitute about 15% of the cases. We didn't mention this because it's still a limitation. Like we couldn't remove these cases properly. I would say that's one case. The third case is obviously pointer analysis. We make use of extensive pointer analysis, but we don't have an expensive, our prime goal was to make sure that we are doing these things faster, and rather than doing some kind of Anderson analysis, which is like too time consuming. So we sort of we chose to, we were willing to take some false positives in this case, given pointer analysis is not a easy problem to solve. Yeah.
Thanks. All right. Let's think about it again.